Okay, so in today's class, I'm going to give you a brief idea about how to install TSMC. TSMC stands for Taiwan Semiconductor Company. 180 nanometer CMOS technology files in LT Spice, and then how to start working in LT Spice. Okay, you can go to this web page. I'll share this PDF, so don't have to note down and just keep listening to what I am telling, and then later. Okay, you can go to my web page on the download section. These are the three. So there is a zip file. Okay, so you can download all these three files in one go, and then zip it. So you have. So this is the .lib file. Okay, lib file contains the spice directory, spice model, and these are the symbols. Okay, .asy stands for the symbols. So having downloaded that, then you can download LT Spice. It is you can go to LT Spice web page. You can download that, and then I think that the LT Spice is also available on my this thing. But you can go directly download LT Spice from the LT Spice web page. Okay. Now after then you install the LT Spice. Okay. You go to the file and you open up a new schematic. Okay. Now once you open a new schematic. Okay, out here, okay, you have an AND gate kind of thing. Okay, that is meant for inserting components. So you need to click on that. So once you click on that, you will get a path out. You will get so many components out here. Okay, these components are they come embedded in the LT Spice. Okay, so NMOS and so many ICs are there here. Okay, these ICs is already there. Lot of things are already there in the LT Spice, but we require, so that is TSMC CMOS and NMOS is not there. We want that. Okay, so that's why you click that. You will see lot of components here. Okay, now why I have clicked it is you need to note down this path properly. Okay, so because once you install LT Spice, there will be LT Spice in so many places, and I think in program files here, 2 or 3 places LT Spice will be there, and then you have to paste this downloaded LT Spice and lib file and the symbol file in the correct directory. So unless you put it in the correct directory, you don't you won't get the simulation. Okay, so that is the reason you click on this, you will get a path. So in this case it is C users and mono documents. LT Spice, generally it will be like that. It will be user, then whatever the name of your computer, then documents, LT Spice, then lib, then symbol. Okay, so there will be a path. So note down this path. Okay, now after noting down this path, so this is the path. Okay, so C users, mono documents, LT Spice, lib, and symbol. Okay, so in this symbol, we paste these two symbols which we have downloaded, CMOS N and CMOS P. They are two different symbols. So we inside this folder we will paste these two. Okay, and then we go. This is lib stroke symbol, right? So you go one level up. You go back to lib. In the lib there are two folders actually. One is sim and one is sub. So in the sub we paste the .lib file. Okay, so once you you go to place this .lib file there. Okay, so after having, then again you open the file once again, and then you have an and the last you have something known as a spice directory. So if you click that, you will get a spice directory like this, a window like this, right? So then you need to write .include TSMC 018.lib. Okay, what is this? This is the name of the file, spice file which we have pasted. Okay, so this is the name of the file, and that is why. So you have to write .include and the name of the file. Okay, so once you do that, you are ready to go. From if you click the component out here, you will be able to get the CMOS N and CMOS P. Okay, so I'll demonstrate to you those things.
Hello.
Yeah, tell me.
Sir, what is this .asy file?
Dot
.asy file.
ASY file. Yeah,
Yes.
I'll just tell you. So, okay, you go to my web page. Okay, you go to downloads.
Okay.
Okay, once you go to downloads, you have this TSMC 180 nanometer folder. Okay, right click on it and you okay. So you have these three files, right? TSMC. Okay, you have this TSMC 180 nanometer zip file. Okay, you can download this, or you can individually. You can download this in a zip file. After doing that, right, you have this extracted on your desktop. Okay, so once having extracted that, you will have these three files. Okay, this is tsmc.lib file. These are the .asv file. Okay, asv file is the symbols. Okay, and this is the technology library file, tsmc 018.lib. So you can open this also. Okay, you can open it on notepad, right? So you will find the model. Okay, so this is presently not required for you, but this is the model file. Okay, so this is like BISP3 model. Okay, that is not what ID equations which we use. It is just a first order, right, or maximum up to the second order. But this model caters for all the short channel effects and things like that. So it's a BISP3 model. On the top it is written BISP3 model, right? So in the ID equations and all, there are so many variables. Okay, so there are so many parameters. So all those parameters are given. Okay, here. So where did these guys? What are these parameters? They have come from the foundry, right? From the actual TSMC foundry. Okay, all these values have been picked up. So that this is for NMOS, and then you have the model for PMOS in the bottom, right? Like Kn, Mun, Cox, and gate capacitance. All these things are available here, right? Now, if you see here, they are all written in short form out here. So if you may not be able to directly tell what it is. So I will share one BISP3 model PDF with you. So that will give you the what these abbreviations stand for. And also, if somebody is interested in knowing the full BISP3 model, then you can go through that PDF. Okay. Otherwise, you have a course of PMMD course, right? Is it a core for all of you? Physics for modeling and of semiconductor devices.
Yes.
Yes.
Okay. So
Yes, sir.
yeah. So there all these physics will be explained, right? But as far as my two courses are concerned, all these things are not required. Okay. As far as I will take MOSFET as a just the basic equation, and I will take it as a black box, and we are interested how that MOSFET can be put into use in the circuits, okay? Analog circuits and digital circuits. Okay, as far as my courses are concerned, all the physics and all things will be dealt in that particular course. Okay, but somebody is interested, then this information is available. So you don't have to open this file. I have just opened it just to give you an idea about how things work in the background. Okay. So this is about the three files, right? Now let me open up LT Spice. The mistakes which people do is, right? I go to File, okay, New Schematic, and then I press this symbol, right? So now you see this path. Users, so you have to note down this path. Okay, see users, this path. Okay, so having noted that down, then I go my PC, see. So if I see, if I go to program files also, there will be some LT Spice here and all. Okay. So CLTC, there is some program file. People go and paste those files there, and hence they don't get the results. So whatever a path is specified here, okay, you have to do it there itself, okay. Unless you do that, you are not going to see. So in this the path has been specified as C users, and then it said documents, right. In the documents I have LT spice. Now in the LT spice there is one lib. Here there are there is one sub file and there is one sim file, okay. Sim stands for a symbol. So I open that and I have pasted that two files here. If you see here, it will be there. I have already done that. So you will find CMOS N and CMOS P symbols. Both the symbols I have pasted it here. Okay. So in my you may not find all many symbols in your this thing, because I have put all this in a 7.4 series ICs and all for my different courses. But you will find few symbols there. Okay. Then I go back. Okay, and in the subfolder, okay, I paste the in the subfolder also. You may not find all these things. I have put lot of model files there, but you will find some of them. So there I have pasted this in TSMC. If you see TSMC, okay, the lib file. Okay, so once you do this. Yeah.
So these two files, these three, whatever we have pasted, we can get it from your website, sir?
Yes, you can get from my web page. I have shown that, right? So you can get it from my web page. Okay. So after doing that, okay, now we are good to go. So let me reduce my mouse size pointer. Right. Then if I go to symbol, so all these components will be there. So initially you will find the CMOS N and CMOS P is not there. Okay. Now they have come. Okay. But you will have here some NMOS and all. Okay. Here NMOS 4, NMOS. So you don't have. These are different things. Okay. For this you have to again specify the spice directory. Okay. For for our use, what we are going to for 180 nanometer, these two have come as CMOS N and CMOS P. CMOS N is NMOS, CMOS P is PMOS. So CMOS N, I click and I paste it here. Okay. Now I will try. If I right click it, okay, I have these. See, this model name is CMOS N. Okay, that it is going to pick it up from that .lib file. There the model name has been specified as CMOS N. So you don't have to change that. Length I will put as 180 nanometer. You can give more length also, but since we are mostly going to work on a digital circuit, we are going to keep length as 180 only. Okay, so let me start putting width as 1 micro. Okay, rest of the information you can give that. Okay, like a drain area, source area. But we don't have to do that. So we leave all those things. Okay, number of parallel devices. We just specify the length and the width. Okay, so now we have specified the length and the width of the device. Now we have to give some voltages and see how this device works. Yeah, tell me.
The length and width we need to give, or we have any lib file for length and width?
No, length and width is a variable as a designer. Okay, when we work on CMOS technology, okay, the CMOS the technology file gives you the minimum length and the width. Okay, so the minimum length for 180 nanometer technology is 180 nanometer. You can have length more than that, but for digital circuits we generally try to minimize the area, so we use the minimum width length. Okay. And for 180 nanometer technology, the minimum width is 400 nanometer. Okay, so 400 nano is the minimum width which is permitted for. So you can give here. Okay, below 400 nanometer, it will do the simulation. But otherwise, since we know that for 180 nanometer, the width is on minimum width is 400, so you need to use minimum width as 400 nanometer, or you can give more than that. Is it okay with all of you?
Yes, sir. Okay.
Okay. So for 45 nanometer, yeah, tell me.
If I give below 180, it won't take, right?
It might throw up some result, actually for 45 nanometer, the this particular lib file which we have pasted, it has been characterized for TSMC 180 nanometer devices. Okay, for 45 nanometer devices, okay, the behavior will be slightly different. There will be more short channel effects and all. So that dot lib file will be different there, right? So here, if you do that, it might put that value, but the character, it will just try to scale down that. It will not take on that additional short channel effects which is likely to come in 45 nanometer technology. Okay, is it understood?
Okay, right? Sir. Okay, thank you.
So we need to use 180 nanometer only. Okay, if somebody is keen on working on 7 nanometer, 8 nanometer, then we have those model files also. We can take it in LT Spice. So I will give a reference of my one other video where I have explained from where you can get 7 nanometer or lower technology nodes also. That also can be done. But that lib file is specifically meant for 7 nanometer. Is it okay?
Sir, if and sir, what about the width?
Related to width, sir?
Width, see, width we need to specify. See, the length and the width, okay, for every technology, they specify the minimum length and the minimum width for every technology. For 180 nanometer technology, the length is 180 nanometer, minimum length is 180 and minimum width is 400 nanometer. So when we design digital circuits, okay, generally we keep the we want to keep the area minimum, so we fix L as 180 nanometer. Okay, width is 400 nanometer, but generally what happens is we will use a higher widths also. Okay, to increase the current levels and for delay compensation. So in this course we are going to learn about how to set the width for different circuits, whether it is analog design or for the digital circuit. We are going to assume length is going to be 180. Okay, that is how the circuits are actually designed, and then to achieve the desired performance, we use width as a variable. Okay, length is also variable, but we fix it at 180, the minimum. For analog circuits, increasing the width, we can increase the width because increased length will give you higher output resistance. We'll see that once we learn the theory. So W and L is a variable given to the designer. So once the technology, a foundry gives right, the model like TSMC model. Suppose I am using TSMC, I am designing a circuit. L and W is variable for me. So I will use whatever length I want for a particular for my design to optimize. I use L and W as a variable, and I will design a circuit. And once having designed the circuit, I will make a layout out of it. Okay, and then send to the foundry. So the foundry will fabricate it based on the length and W which I have specified.
Sir, width means diffusion.
Hello, sir.
Right now, sir.
Width means channel width.
Length
Sir,
is poly.
Channel width.
Can
Length?
you please, sir, explain length and width in terms of
Sir.
how it goes in terms of CMOS?
Okay.
Sir, we are saying
Basically what
AMD
it indicates.
7 nanometer
Sir,
technology.
Yeah,
What is
yeah,
that
yeah.
meaning, sir?
Yeah. I'll take 2-3 notes and then I will explain. Yeah, the second person can go. Go ahead.
Hi sir.
Yeah.
Sir, why length is 180 and width is 400?
Okay.
It will be more than, yeah sir. My doubt is like why it will be like this only.
Okay.
Length will be 400 and width is 180. Why we didn't give like that?
Okay. What else? What is the third?
Sir,
question?
one more doubt. This 180 nanometer length which has been given, it is given in the lib. What about the width, like the minimum width that is, you're telling that it is 400 nanometer, it is given in the lib, or we should know, means where we'll get this information?
You can
Sir, my question-
have a look at the model file in the lib file. I don't think it is specified there, right?
It is not specified, okay.
It is not specified, but generally these things are published by the companies. Okay, right? Okay. Now
Okay.
let's first try to understand what this length and width means.
Sir, length means poly. Am I right, sir? It show the poly length.
Okay, I'll just tell you what it is.
Sir, I have one question, sir. AMD 7 nanometer technology means what they
Just
are
give me 30
mentioning.
seconds. Let me first
Yes, sir.
explain this length and width, and then.
Yes, sir.
Sorry, I'm not sure.
Okay. See, this is how a MOSFET looks like. Okay. You have a source, you have a drain. Okay, and in between you have a channel. On the channel you have an oxide layer. On top of that you have a gate. So this is known as the length of the channel. Okay. So if you have smaller length, that means that device is shrinking. You can have small size of from 180 nanometer to 45 nanometer means the entire device will be almost 1/4 the size. So we are as we move from one technology to other, the minimum L, okay, is defined by the lithography actually. Okay, how it depends on the technology. Okay, so as the technology is moving forward, we are able to make small devices. Okay, so this L corresponds to the distance between the source and the drain, or this distance is what is L. Is it clear to all of you?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So when I say 180 nanometer, okay, so this was the size. Now I have 7 nanometer technology. That means now I am able to fabricate very small devices. Okay, the technology is much better now. Now I have lasers which can make these small masks, a very fine mask, and that when we see the technology, things will be clear. A time being is definition of L is clear to all of you, right?
Yes, sir.
Okay.
Yes, sir. Yes,
Now
sir.
this L is a minimum. See when I'm sending it to 180 nanometer foundry lab, okay, they say I have a technology of 180 nanometer. That means minimum length and I can fabricate is 180. Okay, but for your design requirement, you might want 360 length. Okay, you can tell that. Okay, so accordingly when they are fabricating, okay, so there will be for each transistor, not that in your circuit you can have millions of transistors. Each circuit can have different lengths also, doesn't matter. Okay, because when the mask is made, accordingly they will make, and you just have to ensure that your minimum length is what is there specified. Is that much clear to all of you?
Yes, sir.
Okay.
Length is
Yes, sir.
Yeah, but practically when we do, especially in the digital circuits, we keep L constant. Okay, once we keep L constant, okay, suppose you have let me give you an example of an inverter. Okay, suppose you have an inverter, right? We saw inverter, you have a PMOS on the top. Okay, PMOS, because of holes, okay, the mobility is slower. So while the output node is charged to high, right? So the PMOS will have it will charge it slowly, whereas the NMOS it will charge it it will discharge it faster. Is it understood what I am telling, or
Yeah,
should I
yeah,
draw
sir.
an inverter?
Yeah, I am.
Okay, so in that case, to compensate that thing, I can have an PMOS twice the width of NMOS also.
Sir, can I ask everybody to mute background sound? We cannot hear your voice properly.
Okay, where is the bag? Now it's gone. Yeah. Okay, now is it okay with all of you?
Yes,
Sir,
yeah.
can
Yes,
you
sir.
repeat, sir, that last one, that disturbances happen, sir?
Okay. So let me just open up some files. Okay, this is how an CMOS inverter looks like, right? Okay, Now suppose I give 180 nanometer here, 180 nanometer here. I give 400 nanometer width, 400 nanometer width for these transistors. Okay. Now what happens is NMOS is faster than PMOS. Okay. NMOS is faster than PMOS. So I will have this fall time very less and rise time very like it will be greater than there. Is it understood? If I keep the
Yes.
same W by L for both this, okay. So now if I want a symmetric response out here, I can keep this W twice that of NMOS, because PMOS is almost a half time slower it is like, okay. Is it okay? So the W I use
Yes.
as a variable for designing circuits, okay. So I'll just okay, as of now, don't get confused too much. Just assume that W is a variable. Okay, I'll just give you one slide. See, you see different circuits. Okay, for different circuits, I keep changing W. This is W. This is 4W. So if you go here, it is 6. These are all Ws. Okay. So how to optimize this design, which we will learn in our subsequent classes. Is it okay? So as of now, W is a variable. Let's stop it at that, and then this is the W. This is the width from here to here. Okay. What is W? Can you visualize?
Yeah.
Yes.
Okay. So
Yeah.
this will be width. So length and the width are variables which we need to set.
Sir, may I know width, sir? Where is it, sir?
Pardon?
Width, where you are showing, sir? Width, that last.
Width, where is width?
Okay.
Width, I want to.
I want to see the width, sir.
Yeah. Okay. I think I closed it.
Is it the channel width you're saying?
This W you can see. It's written W.
Yes.
Yes.
Okay.
That gate, sir. Okay, okay, sir.
Yeah. This is the width. This is the length.
Okay, sir. Thank you, sir.
Okay.
Okay, thanks.
So if you generally if you increase W, the current will in the current equation W is in the numerator. Okay. So the current is directly proportional to W. Is it okay? Okay. Now
Yes, sir.
what I do is I'll put some ground out here. So how to put the ground? This is the wire connection. Okay. So you click on that wire, you will get here. So I am going to put this here. Right. I am making this body also ground. Okay. Now I have to now I have just given the source as ground and body as ground. Now I need to connect voltage sources. Okay. So now I click on this again component. Okay. And I scroll here. I will find there is something known as voltage. Okay. I take voltage. So I place the voltage out here. Okay. Now I am going to give an ground here. Right. I am going to give a ground here. Okay. Now having given ground here, so let me give, this is known as move. Okay. This is known as drag. Okay. So the difference is if I click on move and if I move here, see the ground has remained there. The individual component will move. Okay. Similarly, if I do here, if I move here, the individual component will move. Okay. But if I put drag, it will go along with the connections. Okay. So
There is no
you want
shortcut keys.
pardon?
There is no shortcut keys for move and drag.
There is something you can probably will show somewhere. There could be some shortcuts also you can Google it. Okay. So now I have put this voltage source. I do a right click. No, it says a DC value. Okay. Now I want to I can give some. I have to give some DC value. Okay. So let me give it as 1.8. Okay. Don't write 1.8 volt and all. Okay. So the units is taken care of. Okay. Similarly, when I am setting this length and width, don't write nanometer. Okay. 180 nano. Width is 1 micro or 400 nano. Okay. So that is it. Okay, that will be enough. So I have put an voltage source here, right? Now I have to put an give a voltage out here also. So I can use this edit. Now
Is it
duplicate.
units by default it will take?
Yeah, it will take units by
Okay.
default. Okay. So I have put an.
I'm sorry to disturb you
Yeah, tell
in
me.
between, but I just wanted to know what is this V1 and 1.8, because 1.8 you put it near to the ground and V1 is separated
Yeah.
near to plus sign.
Yeah. Okay. One point is the DC voltage which we have set. V1 is the name of this source.
Oh, okay.
Okay.
Okay, so I
Here-
thought like it's given at plus V1 and minus 1.8, that's right.
Yeah. Okay. Now suppose I give it as an minus 1.8. Okay. You see this voltage level is minus 1.8 here out here. Okay. V1 is the name of the source. Okay.
Is the
Thank you,
current
thank
flow
you.
according to the width of the channel?
Pardon?
Is the current flow according to width of the channel?
Yes.
Is this
In the
right, sir?
ID equation which we will learn. Now, okay, I is proportional to W and inversely proportional to L. We will learn that. Okay.
Okay.
Now this V1 also. If I have to change the name of this source, now if I right click it, I will get only DC value. I can go to V1 and click on right click. So let me write it as VGS, V gate source voltage. Okay, and this is V drain source. So let me click on it, V drain source. Okay, that I can change the name of the source. Okay, now I put this here.
For writing, what key you press, sir?
Just right click there.
Okay.
Okay, this is the label of this here. Okay, this is 1.8, 1.8, right? Now I have to do an DC simulation and see what happens if I change the VGS values from 0 to, right? So
Sir, how did you copy paste the voltage source
see
in the?
edit and duplicate,
Okay, okay, okay.
right? So this is there. So I can have edit and view zoom to fit. Okay. So again, then I can just scroll little bit to. I can use the scroll thing. I have to put it now. This device I have to specify the this thing. So I have to write dot. See when you take this, okay, there will be one comment and one spice directive. You know you have to select the spice directive, not the comment. So dot include TSMC 018 dot lib. Okay, so I put that also there. Okay, now I have to now if I have to run the simulation, I have to change some variable, right? So what I do is right click, okay, edit simulation command. Okay, so I can do that. Okay, I can either do that or I can go to simulate control panel. Okay, both I'll get these. So let me show you. Right click, okay, edit simulation command. I am going to do a DC sweep. Okay, which source? It says name of the source to sweep. So I write an VGS. Okay, VGS I want to sweep. What kind of sweep? I want to do a linear sweep or an other sweep. So I want to do a linear sweep. I want to start from 0. I want to stop at 1.8, and I can say 0.05, every 0.05 voltages it has to do. So okay, so I'll get this. Okay, so now this is, now I run the simulation. So once I run the simulation, I'll get this in a simulation window. Now to plot the currents, okay, there to plot the voltage, okay, you have this pen kind of thing. Okay, it is not actually pen, it is that what Holika Pichkari kind of thing, right? So I can take that onto the wire wherever I want the voltage. Okay, I click there, right? Now you see this voltage has gone from 0 to 1.8 volt, isn't it? Okay, that is what we have given. So here it is 0 to 1.8.
Sir, what is the importance of DC sweep?
Because I am doing an when I am doing an DC analysis, I am changing some DC value. All the capacitances will be considered as an open circuit. Okay, in the left axis there is no time. Okay, it is just the voltage. Is it okay? When I talk about other analysis, you will understand the difference. Okay. Now I have to plot the current also, right? So for the current, you see this. Okay, this was voltage. For a current, you see there is one ring kind of thing which is coming, right? Okay, I see some kind of a handle and a ring. Okay.
From where we have to select current and voltage?
You just take your cursor to those places. You will get these things coming up after the simulation. Okay. Is it okay? See,
Okay.
Yes.
let
Yes,
me
sir,
close this. Now I have not run a simulation. Okay. Now if I put this cursor, I won't get those symbols. Okay. Once I run the simulation and I have this window, after that if I put this cursor, okay, I will have these things. Okay. Now if I put it here, I see this thing, right? This is the current. It is in from 0 to 300 microamperes current. Is it okay with all of you?
Yes. Yes.
Yeah. And all in this particular case, okay, the voltage is already there in the x-axis. Suppose I want to plot the voltage also for, okay. So this is the voltage also. So here I have voltage, here I have the current. So there are two windows. So I can do a right click, add plot pane, and just drag this there. So this is the voltage and this is the current, VGS. Can you see that?
Show that again how you separate.
Continue, please.
Yeah. Okay. How I separated is right click, okay, add plot pane, a pane. So you will get one more pane. So you can keep moving this, right? You can put it together or you can move it separately. Is it okay?
Sir, all graphs are drawn against the voltage.
Yeah, here because what variable I have set here is voltage.
Okay, for the DC sweep you set it as voltage, so even when you draw the current, it will be against voltage.
Pardon?
So since you set the variable as voltage, when
Yes.
you draw the current also, it goes against voltage.
Against voltage, yes.
Thank you.
Sir, when you specify this VGS voltage, what is the significance of this 0.05? Means is the interval 0.05 or?
It is doing a simulation at this is not continuous. It is doing at 0.000 every point. If you take it as let me take it as 1. Okay. If I do, right, you will see, okay, this is taken first point here, second point here, third point there, right? Step size.
Okay. Understood. Okay.
So I am giving a step size of increment, that is 0.05, so that I get a better curve. That information is not lost. Okay. Anybody else has got any doubts in this?
Sir, from where graph curve comes, sir?
Pardon?
Graph comes from where, sir?
Pardon?
Graphs curve from where?
Graph?
Yes. Yeah. Graphs comes from where, sir? This one. How?
This graph.
Where we touch? Yes, sir.
See, see, once you draw this, right, you do a simulation, it will come up once you run this.
Simulation.
Sir, one more graph, how it will come, sir?
See,
where to right click and
I have done the run. Okay, now I am plotting VGS. Okay, VGS is changing. I am plotting current. Okay, so both of them have come in one plot. I do a right click, add plot pane, and I can take one of, I can just drag and put the one onto the next pane. Again, if I have many,
yes, sir, that is only towards add plot. Okay, on graph only we have to select.
Yeah.
Okay, sir.
Is it okay?
Yes, sir. So we are trying to plot the current, right, sir, by applying the voltages, right?
Yes. Right. Now I can also see, but this 1.8 doesn't have any value. Okay, because I am sweeping it. Okay, but suppose I am doing an AC analysis. In that case, it will take this value. Okay, it will do a simulation for 1.8. So you need to you have to specify these values. Okay, that is known as the DC operating point. You have to give, although okay, you are sweeping. Now suppose I want to sweep instead of VGS, I want to sweep a VDS. Okay, let me give VGS as only 1 volt. Okay, and VDS I want to sweep. So I can go and change this as VDS. Okay, and if I plot, so this is ID VGS, ID VDS curve. It looks like this. Okay, why it is looking like this and all we will learn in our theory class. Okay. Now if you see this is what VGS. Now we have we are sweeping VDS, and hence VGS is constant out here. Correct? We are not sweeping this. We are sweeping this. This is constant 1 volt. So here we are getting constant 1 volt. Okay, and here we are getting a curve. Is it okay with all of you?
Yes.
Okay.
Yes.
Okay. Now I go to this this thing. If I have to say I want to know at 1 volt what is the current. Okay. So what I can do is I can right click on this. Okay. Here attach cursor. So there is an option of attaching 1 cursor, 2 cursor. So I can attach only 1 cursor, or I can attach 2 cursors at one go. So first and second. Okay. So I can now move this cursor. Okay. So 1 cursor I have placed at 1. Second cursor I have placed at 1.2 volt, and I have a small window here. It says okay, for 1.2 volt 95.9 is the current, and for 1 volt the current is this. So for both these cursor, the horizontal and vertical values are known here. Okay, and you can move this cursor anywhere along this graph to note down the readings out here from this window. Is it okay? So the procedure is go to ID, right click on it. Okay, attach cursor. Okay, so you can attach. If you attach only 1 cursor, you will get only 1 cursor. Okay, so there is only 1 cursor. If you want to attach 2 cursors simultaneously, you can do first and second. Okay, so you will get 2 cursors. So you can move this cursor along this graph anywhere and get the values. Is it okay with all of you till here?
Yes, sir.
Okay.
Sweep is the step size, right, sir?
Pardon?
Sweep is the step size, right? Sweep. Name of the source to sweep. We are giving the value, right? Sweep.
Here, right? Here, if you see here, name of the source to sweep is the name of this source.
Name of this, correct.
Okay, what you want to sweep. Okay, right? Okay. Now, when we make digital circuits, okay, you can have A, B, C, D inputs. You have a complicated circuit. Okay, then from that A, you want to give it a 10 different transistors. Okay, so every time drawing wires, okay, will make it a very it will make it shoddy, and there you are likely to take make mistakes also. So there is an option. Okay, what you can do is, okay, you put the source here. Okay, right click, label net A. Okay. Now one more thing which you need to remember is, see, I am drawing a line out here. Okay, I am putting a wire here to here. I have drawn a wire, okay, but that wire has actually not got connected to the gate, okay. If it is got connected to the gate, this square thing will get disappeared, okay. So this is actually not got connected. In fact, you have to take care here also. So it is better to connect it like this. So if you see those squares, it is possible that the connection is not made properly, okay. Here it is okay because it's an intersection of wire. Here if you see here, right, this is how the initially transistor will look like, right. If I remove this, see there is a square here. If I remove here, there is a square, right. They are all open. So the moment you connect a proper wire, okay, that square disappears. Can you see that? Right. Okay. So I am putting a wire out here, right, and I am giving the label as A. Okay. And I do the simulation, okay. Again I am getting the same graph out here, right. I am not getting here because this one because now I have labeled that the thing. So if I have to have plot, I can plot A out here. So I will get that A 1 volt what I was getting here. So instead of you can put all the sources in one place and name them A, B, C, D, and then give the net name. So this A and A they get connected to each other. Is it okay? Understood, right?
It means we don't want to connect by the wire. It's if I give a label name A and A, it's connected.
Yes.
Am I right, sir?
Yes, they get connected. Okay. So,
For label, right
Hello,
click
sir.
on the wire label.
Yes.
Is it connected automatically?
Yeah, the system
by
will take it
giving the
because you have
label?
given the same label name.
Label. Okay.
Okay.
Thank you.
What many students do is they will go and they will change the name of the source as A, okay, and then they will not give a name here, okay. This doesn't get connected, okay. If it is A, you can give this A, no problem. But if you want to get these two connected, you have to give a wire label to the wire. Okay, so the wires they will get connected. So this is okay, perfectly fine.
So, sir, for example,
Yeah, go ahead.
for VDS voltage and VGS voltages are same. Okay, if I want to connect both by using only one source, this one A, I can make A over there and here as well, right?
Yes, correct. So let me show you some.
Okay.
This is full adder, okay. So I am giving, this is my A, this is B, this is C, okay. So I have given A at many places. So all of them are interconnected. Okay.
Okay. Understood.
Right? Okay.
Yes.
So you can do that.
Okay, sir. Thank you.
Okay. So let me close this.
Sir, so what is the use of the label? Basically, we are using it for creating complex circuits.
Correct.
Okay.
Right. I just showed you full adder, right? If you
Yeah.
start drawing wires everywhere, right, it will become clumsy, and if there is when you are crossing the wires, if there is an interconnection made, then you diagnosing it will be a difficult task, right?
Yes.
Right.
Okay.
But
Thank
the
you.
system when it is simulating, it will assume they are connected. Okay, in the background.
Okay. Yes.
Okay. So now I have done include TSMC. Okay, I have let me take this particular case. Okay, let me call this this is 1.8 volt. Let me call this as an VGS, okay, 1.8 volt. Let me call this as VDS. This is VDS. I'm going to sweep VDS. So let me sweep VDS. Okay. Now I want to sweep VDS and I want to see now what happens if I change VGS, okay, for different VGS values. Okay. So what I can do is I can right click here, okay, and within flower bracket I can make, instead of 1.8 I can make it as some variable. Okay, let me take it as VGS itself. Not necessarily VGS. You can do, you can give any variable name. So I have given it as VGS. So let me just call this as an V dash VGS. Okay. So this is VGS. Now I have not specified the value of VGS. Okay. So now I am going to include one more spice directive. Okay. That is again from here spice directive. I am going to type dot step parameter VGS, okay, 0, 1.8 in steps of 0.2. Okay. So it is not this VGS. Okay. This value of the VGS I have given within flower brackets. Okay. That means this is going to be a parameter now, right? Now if I run this simulation and if I plot the current out here, so you see these are what? The first run, okay, is for VGS is equal to 0. The second run is for VGS is equal to 0.2. The third run is for VGS is equal to 0.4 and it has come up to 0.8. So this is how I get the multiple plots single run. Is it okay? Is it understood what I have done?
Sir, I have one question.
Yeah. See, I am sweeping VDS, but for every run I want to change the value of VGS. Okay. So I am doing step parameter. Step parameter means initially for the first run I will take VGS value as 0 and I will do a VDS sweep, DC sweep of VDS from 0 to 1.8. Okay. In the second run, okay, I will do I will increase the VGS by 0.2, again I will run. Similarly, I will keep increasing in steps of 0.2 till I reach 1.8. Is it okay?
Yes.
Yeah. Anybody else has got any doubt?
Sir, I have one question.
Yeah.
Why we are writing these commands? Like, what is the significance, and can you please explain this? Like, this is
these commands are to this is setting up the simulation environment. Otherwise, what simulation it will do? It won't know what to do, right? So we are telling the software to do this.
Okay. So we have to we have to learn all these commands, or like anything for
there
that?
are not many commands. Okay, I'll share this files with you with videos. There are not many. You'll get used to it. Okay.
Thank you, sir.
Okay.
Sir, hello.
Yeah, tell me.
So in the current run, the VGS and
just
VDS.
1 second. 1 second. Hello, I'm in the class. Can I call you later? Who is this? Yeah, I am in the class. Can you just call me in the evening? Yeah, tell me. Somebody had a doubt.
Yeah, hello. So in the current run, both VGS and VDS both are varying, right?
It is like once in the step parameter, it is not varying simultaneously. In okay, what is set in the step parameter, it is taking first fixing that value VGS is equal to 0, completing the DC run, then changing the value of VGS, again completing the DC run.
Okay. And please, can you please explain what is the difference that V dash GS and the curly braces you are giving?
No, nothing. This is the name. Okay, this is the value. So when I write step parameter, okay, the value, this value what I declare, okay, I can write it as X also.
Okay. Okay.
Then this will become X. Okay.
Okay, okay.
Why? Because this is not going to change in the step parameter, right? In when I'm writing a DC, right? VDS, right? I'm picking up some noise. Okay, anyway. When I'm doing a DC run, here it is the name of the source, right? This VDS, name of the source, right? But when I am doing parametric analysis, it is the value of that, okay, within curly bracket. Is it understood the difference?
Yeah.
Okay. Within so this step parameter, if I put one more curly bracket here instead of 1.8, okay, right? If I put an x, this and this simultaneously will change. Okay, so that will give an erroneous results. Okay, so you have to in the step parameter you have to match this. Okay, see this, right? You get this result.
Sir,
right?
sir, so here in curly braces we are placing the value.
Yeah. For each run. This is the thing. Dot DC is the command in which one parameter is changed during a single run. Step parameter is for different runs.
Okay.
Okay.
Okay, sir.
Okay. So,
sir,
now,
one question.
Yeah.
So instead of making these circuits, can we directly write a spice code for this?
Probably it's possible, and I have not tried out. Okay.
Okay.
It is possible. So, if you go here, I think you can. There is somewhere it shows the legend also. Plot settings, because you don't know which is this run. So, add cursor, tool simulation, plot settings. View, zoom, reset colors. There is somewhere notes and annotations. Grid auto range. You can actually can see the legend, right? What these colors are for corresponding to which run. That you need to know that also, right?
Sir, shall we click on that color and we get the values?
You can put a marker, but
Yes.
I am looking for an. You will get the total legend also. View somewhere. You get the legend and a step. Step legend. Okay, here. Right.
Yes.
So here you get right. X is equal to 0. Run 1. X is equal to 0 is green in color. Right. Run 2 blue. Now this is blue. Okay. So all that legend you will get from here. Okay. So let's see.
Sir, can we make the bold colors? I mean, the colors will be in bold.
Yeah, you can do that. Okay, you can right click and some trace properties are there. So you can do that. Okay. Now this is for a PMOS simulation. Okay. For a PMOS simulation, okay, you have to change the drain to source to. So the for a PMOS, the source is on the top and the gate is out here. Like so, when it is 0, the gate to drain voltage will be 0, right? Right. Like if this is 1.8, here I am giving 1.8. So when it is when this V3 is 0, okay, what will be the gate to source voltage here? It will be maximum.
It's maximum, sir.
Yeah.
Yeah,
And then when this is going to 1.8, what will be this?
Zero.
Minimum 0.
Minimum, right? So can you just tell me how to edit the command, this command, what I need to do? Here.
V3.
Yeah, V3. V3. Okay. Correct? Because I am going to sweep this voltage, right? So I have given V3. So I do a simulation and then I plot a current out here. So if you see here, it is an 0 out here, right? And this is the again ID VGS curve, right? So
Yes, sir.
Similarly you can get for PMOS. Okay. So let me show you some other simulations also. So this is where am I picking this noise? I think it's from here. Yeah. Okay. So this is an inverter. Okay, I have given the DC value as 1.8. Okay, this is the name of the source. This wire name also I have given V in. Doesn't matter. Okay, so let me just not to confuse you. Let me. Let it remain, doesn't matter. Edit, undo. So all those things are there. Okay. Now NMOS. Okay. Let me give it as 400 nano. Right. PMOS. Now let me give it as 800.
200.
No, 400 is the minimum. So PMOS is slower, so I am giving it as 800. Okay. So this I have given as VDD. This is V in. This is an V out. Okay, I am sweeping a V in from 0 to 1.8. So I do a run. Okay, and I measure the output. So this is the output graph. You see V in going and coming like this. Is it okay? Is this graph understood? When V in is 0, now V out is 1, and as V in is increasing, V out is coming to 0. Okay. So this is how we do a simulation for the inverter. So we'll learn all this theory. I will share this video with all of you and the PDF. So as and when the theory is covered in the class, you try out this simulation. So you can this video will be available with you always. Okay. So that is V in and V out. If I have to find out the currents which are flowing in this circuit, okay, so I can plot the current also. So this is the symbol for the current. So if I press that, okay, I'll get this current also, right? So if you see when both PMOS and NMOS are operating, okay, there is a spike in current. So I can go here, right click, and I can attach one cursor. Okay, so this is a cursor. So I drag this cursor through mouse. Here I will find that it is 61 picoampere. As I keep moving this cursor, the current is going high. It is going up to 54 micro, and then if I again keep moving towards that end, it is again come to 19 picoampere. So this is how we plot the currents. Is it okay with all of you till here?
Yes, sir. Sir, one question.
Yeah.
You have not defined the step size for V in sweep. So what is the default step size?
You can do. I think I'm not sure what default value it has taken. We can do it. Right. Doesn't matter. So right, you can define that. If you leave it, it will take some default value. I'm not sure what it has taken. Okay. Okay. So this is how we find out inverter, right? Now, like I said, this we will study subsequently. Okay, once in the theory, then it will be understood by varying the width of the transistors. Okay, like if I put the okay, if I run it, the VTC curve will keep moving.
Sir, this W, is it same for both PMOS and NMOS, or that also we can vary differently?
No, at any one point in the parameter you can set only one parameter to be changed, that is W, right? You can give W at n number of places, all those W's will change, but I want to see actually, okay, the difference in the VTC curve when the ratio of W of these two are changing.
Okay.
Right. So just to we'll study these in details, but just to give you a hint, if NMOS is stronger means width is more, then will it take that much more voltage for this output to be start falling, isn't it? Suppose it is 400 nanometer, okay. So if it is 400 nanometer, this will be the graph. Now if I put right, if I make PMOS very strong, okay, or if PMOS is very strong means W is large, it can put more current, then it will take that much more input voltage for this to fall. So accordingly, this graph will shift here and from here to here. So that aspect we will study in our theory classes, and then you will be able to analyze these kind of simulations. Okay.
How did you plot the ratio between the? How did you plot that exactly?
Well, I have this width I have fixed at 800. This width I have given it as a variable.
Variable, okay.
Okay, and I am setting it the parameter. I am starting from 1 micro to 10 micro in steps of 1 micro. Okay, I can do that kind of thing. Okay.
Yes, sir.
Is it okay with all of you?
Hello, sir.
Yeah, tell me.
So for practicing and doing assignments, where we will be getting this LT Spice, we have to download it.
Which files?
LT Spice, this simulator.
Yeah, you will have to download this.
Okay,
right?
Thank you.
You have to download the TSMC file from my web page, and you need to download the LT Spice from their web page. And then once you have installed, then you don't require internet connectivity. Then you can keep doing it at your own place. Okay.
Okay. Thank you.
Okay. So this is about DC simulation. Okay. Now we were doing only DC simulation till now. Now there is something known as a transient simulation. Okay. Now I am not giving a DC voltage out here, but I am giving a time variant source. So where did I get this time variant source? So I go to source, okay, I go to voltage, I click, I get a voltage source, right? Now I right click it, okay, there is something known as advanced. So if I click on advanced, there are a lot many sources available here, right? I can have a sinusoidal source. I can have a, so I am going to use sinusoidal source for my AC simulation, okay, for my analog circuits, okay, but for digital circuits I am going to use pulse. We are going to use sinusoidal signals also for our analog classes. I will explain, I will give demo once we learn little bit about the circuits there. But time being, to start with, let me just show you how to give a digital signal. So I given pulse, okay. Now the V initial, okay. So actually there are two values, right, in a pulse. One is V initial, V1, V is on, okay. So I can give 0 and 1.8 volt, right. I can give 0 here and 1.8 volt, but for some reason, okay, in LT Spice it starts with V on and then it goes to V initial. So I am giving it 1.8 and 0 here. I am not going to give any delay here. I'll explain you what a delay is. Rise time I am giving it as 1 pico. Fall time is 1 pico. On time is how long this pulse has to remain high. I am giving say 10 nano and period is 20 nano. Okay. So that is how I set this. Okay. In this particular example, here what I have set is, okay, initial is 0, on is 1.8. I have given a delay of 500 nano. Let me not give that. Okay. Rise time is 1 nano. Fall time is 1 nano. T on is 1 micro. T period is 2 micro. Okay. So I run the simulation. First, let me see what kind of an input signal I am giving. So I am giving this input signal. Okay. So why I said is like T, if we give the pulse as 0 and 1.8, it will start with 1.8 and go to 0. So I am giving so that's the reason I said let's start with 1.8 and then give 0. Okay. Then it will give 0 and then it will go to 1.8 volt. And then total this is 1 micro from here to here. Okay. And here to here is 2 micro. Because that is what I have set here. Okay. On time is 1 micro, total time period is 2 micro. Is it okay? And this rise time is so and then I also have to give this dot tran. Okay. Where did I get that tran? Right click, initially edit simulation command. We did DC DC sweep. Now there is something known as transient. In transient, I have to give the stop time. So I can give stop time as 4 micro. Suppose I give 4 micro and I run the simulation. So I get 4 micro. So I am getting 2 cycles here. So one is 2 microcycle, another 2 microcycle. Is this clear to all of you?
Can you explain once?
There is a change between initial and on, right?
Yes.
That I didn't get actually. You are swapping the values.
Okay. Right. Okay. Now here I have given. Okay. See what are the properties. Let me compare. Okay. V initial 1.8 volt. So this is taking 1.8 volt. V on is 0. It is 0 here. Right. This is actually swapped for some reason in LT Spice. Okay. V initial and we need to give 2 voltages for DC voltage, right? 0 and 1.8 volt, right?
Yes.
Okay.
So why we need to swap that actually?
Here? No, you can do that also because I want to see 0, 1, 0, 1 a waveform like this. For that reason. Okay. If I give here 5, okay. If I give 5 here and run it, then it will be 0 and 5 volt. Because I am working in 180 nanometer, I am giving it as 1.8. Okay. Yeah, tell me.
Sir, in this graph, the rise and fall I cannot see, right? It's the it is taking the ideal case. But we have given 1 nano, right? Means the signal will take 1 nano to rise it to the. So in the graph, is it not visible, right?
It's not visible.
Means
you want to see that?
Mean
I'm giving it as an say a 0.2 micro rise and 0.2 micro fall. Okay. I do.
Okay.
Now you can see the rise and fall.
Okay. Okay. Fine. Yeah. Okay.
Yeah. Okay. So now let me revert back this to 1 nano and revert back this to 1 nano. Okay. And T on is 1 micro and T period is 2. Okay. So let me put T on as 0.5 micro. What happens? Okay. So I have an asymmetrical T on. You see this is only 1 micro here. Okay. T, this is 2 micro. This is just 1 micro. So initially I had given symmetrical values. Now if you give this as 0.5 and 2 is the total time period. So you can set these values accordingly. Okay. So is all these parameters understood by all of you?
Yes, sir.
Okay. Now only thing which we didn't discuss is delay. Now you see this is starting from here. Okay. I can give say 2 nano delay also. Okay. So if I run that, okay, I have to give 2 nano won't be visible. 2 micro. Okay. So it has actually shifted from here to here. Okay. So you see the graph has shifted. So when you give multiple graphs and multiple sources and you want to do a phase shift between those graphs, so you can give some kind of a delay, okay, for these sources. So is this delay understood by all of you? Okay, it has started after 2 micro, so that kind of delay you can set. Is it okay?
Yes, yes.
Okay.
Sir, here we have set the delay of 2
micro.
So if it is starting after 2, right?
Yeah, yeah.
Okay.
So
sir, in general, these values by default, who will set, sir? Actually,
you will set. As
user
per your
will
assignment.
Correct.
Yeah, there is nothing. It will be blank initially. Okay, you'll have to set this.
Sir, will they be given in the question in assignment these values?
Don't worry. As we move ahead, you will understand. You will know what to do. Don't worry about it.
Okay.
Okay, I'll be giving a demo as and when required. Okay.
Okay, sir. Okay, thank you.
Okay. So we talked about how to give pulse. Now after giving that, we have to do some measurements also, right? So,
sir, one question here. So when you give the delay, what is the value being considered during the delay time for that particular source?
No, delay is just shifting that on the time axis towards the left or right. Okay, that is nothing, not propagation delay or something. Only the input signal reference. We are adding some delay. We are set a waveform. You have to give some timing. Let's not get. We'll think about the delay later. Delay is 0 in our cases. We'll start with there. Okay.
Okay. Yeah.
Okay. Now this tran. Okay. This you can do it for 8 micro also. If you do that, you will get more number of cycles here, right? So that is trans. Okay. Now I have to see input and output. So to see input and output clearly, let me just take only 4 micro out here. So I am plotting input. I am running it. I am plotting the input and I am plotting the output. So here add plot plane and I am just pushing this out. So this is the input and this is the output. You see they are inverted. Correct?
Yes.
Yeah.
Yes, sir. Yes, sir.
See that. Now, if you have to find out the propagation delay, okay, I can put here because there is no capacitance connected. You will find that there is almost no propagation delay. Okay, you can put I can put one cursor here. First cursor. Okay, I move that. Sorry. Okay, I can take this cursor. Actually, you will have to do a lot many steps. Okay, so you have to place this cursor somewhere in between, and you have to place the second cursor in between, and you have to find out the time difference. Okay, so it is slightly difficult in LT Spice. Okay, because you have to give so many small steps. Otherwise, what will happen? This cursor will jump from here to here. Right, so that is the reason. Otherwise, this is where you find out the propagation delay. In this case, since there is no load connected, right? So and hence, the propagation delay is very negligible. But if I suppose if I connect a capacitor, okay, and I put a ground here, and then I take here, right, and then I put this value of the capacitor as say 10 nano, okay. So I put a load capacitance. If I do the simulation, okay, it's not able to drive at all. This is very large capacitance, okay. So let me put it as 1 pico. Pico is too small. Let me put it as 100 pico. See, okay. Can you see the output now? Right? Because this is right. Because I have put a capacitance. Now it is taking it is getting charged slowly and it is getting discharged slowly. Okay. So you can see that, and then if you have to find the propagation delay, you can put you can move this cursor somewhere, see halfway through, right? So this is making a transition here at 1 microsecond, whereas it is reaching 0.9 value of 0.9, 0.8, 0.9 at at 1.15 microsecond. So 0.15 microsecond, that means 150 nano is the delay, propagation delay here. Similarly, here between this edge and this edge, you can find out the propagation delay. Okay, so this is how we find out the propagation delay. Is it okay with all of you?
Yes.
Okay, right. Now, if I have to find out the power also, okay. So what I can do is I can plot the current. Okay, one option is, okay, if I plot the current which is coming from this source. So if you see here, this current has been plotted out here, this red line. Okay. So let me first show you without this capacitance. Okay, so this is the current. So whenever there is a transition, okay, there is a current flowing into the circuit. Okay, otherwise, if I put an see here the currents, if I see on that small panel towards the right hand side bottom, okay, I can see the currents out here are a few nano ampere only, pico ampere. But here, okay, whenever the circuit is making a transition, it is in micro amperes. Okay, so these are the currents. You can plot these currents. Okay, now this current is this current, right? This current multiplied by this voltage will give the power, right? So that is one option of finding out the power. Okay, the other option out here is I press Alt, okay, and once I press Alt, I get this thermometer kind of thing. Okay, so if I put this thermometer and click on this PMOS, okay, which is M2, the name is M2, so I'll get directly the power. Okay, let me close this. Okay, I am plotting. I'm running the simulation. I am plotting V in, I am plotting V out, and then I am plotting the power. Okay, so for power, I am pressing Alt and taking near the device, so I get this thermometer. Again, I am plotting the power from NMOS, and I am taking the power of the source also. So if I do that, and I'll get all the powers. So I get add plot plane, add. So this is my V in, this is my V out, which is an inversion of that, right? This is my power supply, power from the power supply. This is the power in the NMOS, this is power in the PMOS. Okay, So if you see here in the NMOS and the PMOS during transitions, there is a power. Okay, that short circuit current which we learned, right? When it is making a transition, there will be some power dissipation, right? There will be current flowing from source to drain. So you will find these power consumption is there. Okay. Now whereas this total power will be equal to this power, but for the power supply source it is showing negative. Okay. Why it is showing negative is because the power is being given by the power supply, and that is why it is showing negative. Whereas the power is dissipated in the NMOS and PMOS. So if you see here, okay, for the NMOS power, here when it is making a transition, okay, this is a short circuit current as well as switching power. So these aspects, as and when we learn the theory, okay, I will explain you all this power in more detail. Okay, all this I will redo all these simulations and I will explain you, okay, why this is larger, why this is lesser, why here it is larger, why it is lesser. Okay, right now I am just giving you a small hint of the tool. Okay, so that you can do some basic if you have some time, because next week we won't have any class. So if you have some time, at least you can install this tool and do some experiment of your own. But otherwise I will revisit all these things as and when the theory is covered. So after every theory, I will show the same thing what we discussed in the theory, okay, with simulations, and we will correlate to all those things. So that, okay, now if you want to find out the average power, you can do control. You can press control and go and click here. So here it will give a value of that. Okay, no. Control. Yeah, it is showing as average is minus 41 nanowatt. Okay, total power taken. Okay, it is minus because the power is being given by the power supply. Whereas for the PMOS, if I do, it is average power is 22, and for this also this average power is around 19. Okay, 22, 19. So what are these waveforms and more explanation? Since we have not done the theory right now, I will not spend time trying to analyze these graphs in details. But you got a hang of the tool, right? Okay, how to plot the power, how to plot the right currents. So if you have to plot the currents also, you can plot the currents also, right? If you take the current. So this pencil kind of thing is for voltage. This round thing is for the current, and if you press Alt, you will get a thermometer kind of thing. Okay, so you can't put a thermometer on a wire. You can put only that thermometer power on any device. Okay, because it is power consumed by that device. Okay, whereas a voltage you can put here, current also you can put on a wire. Okay, so these are some of the basics of the tool. So so I suggest you download it and do some basic simulations, but and then keep things ready as and with each theory class in whether it be in a VLSI or analog IC. We will do some simulations and try to consolidate what theory we have learned by doing a simulation and verifying the results. Okay. So I think we'll stop it here. Thanks a lot.
Sir.